All right, so we do address the topic of precision and accuracy in our note packet on page 3. Remember again that the precision is how close the values in a set of measurements are to each other, and accuracy is how close these values are to a target value, toward the true value, to the accepted value, the quote-unquote right answer. How close are the values to that? All right, you don't have to even know the true value in order to be able to figure out how close the values are to each other, and we can quantify that using the standard deviation. I have another video showing how to calculate that both manually and with a spreadsheet. And when we calculate that, we're calculating how close they are to each other and to the average value, which is sort of the midpoint of the set of values. Okay, I'm going to try to get another video about the meaning of standard deviation, but in general, you can expect that most of the measured values will lie within 2 standard deviations of the average. So here we have the average in the middle, and most of the values are going to lie within this range. We have +1 standard deviation, +2 standard deviation. So we have the average +2 standard deviations. This is supposed to be a D. And here we have the average -2 standard deviations. So this range that most of the values are going to fall into is the average ±2 standard deviations. So if the standard deviation is 2 points for this example, so our standard deviation is 2, then 2 times the standard deviation is 2 times 2, which is 4 points. So for this first case, where the standard deviation is 2 points, then that means that this range is ±4 points of the average. So that's a pretty tight range for a bunch of exam scores. So we have 2 standard deviations, which would be the average ±4 points, because the standard deviation is 2 points, so 2 times the standard deviation is 4 points. Okay, the average we say is 85, so the scores are 85 ±4. 85 minus 4, it looks like the low score was close to 81, and the higher score was 85 plus 4, 89. So we have, again, a pretty tight range of scores in this set of exam scores. Almost everyone scored within 4 points of the average score. We have a second scenario here. We have a wider spread of data. We have a standard deviation of 10 points. So that means 2 times the standard deviation is 2 times 10 points, which equals 20. So we have everyone scoring within 20 points of the average. So this time the range, average ±2 standard deviations, is average ±20 points, because our standard deviation is now 10 points. And in this case, our average is a 72. So this set of exam scores is 72 ± 20 points. 72 minus 20 points is a 52. 72 plus 20 points is a 92. So here we have a much wider spread, people getting between 52 and 92 points, versus here where people got between 81 and 89 points. So I have already posted another video with calculating the standard deviation and the average, and so I will just direct you to that video and to the answer key for the notes in order to get the answers to A and C. All right, so I think that we need to actually look a little bit at A, because we need the average in order to get B. So what we need to do is add up all these data measurements and then divide that by the number of measurements we have, which is 5. When we add these up, we actually get a result with 5 significant digits because all of these are 2 past the decimal. So we have 50.016 grams, and we can keep all 5 of the significant digits in this case because we have a number with 5 significant digits now in our numerator, an exact number in our denominator, infinite significant digits, so we can keep 5 significant digits in our average. Okay, so to calculate the percent error, we're seeing what the difference is between our measured average here, the average mass that we measured, which is 50.016 grams, and the true value, which is accepted to be 50 grams because it's a 50 gram mass. So we're using this for calibration. We're counting on this to be 50 grams. These lines here are absolute value bars, so we are just trying to tell how far apart these are, not whether this comes out to be a negative or a positive number. We're just going to use the magnitude. It's going to be positive no matter what. Even if this were 49, we would just report this numerator as a positive number. That's what these absolute value bars in the formula mean. Okay, when we do this, we get 0.016 grams, but since this is only known 2 past the decimal, we are now limited to being 2 past the decimal. I'm going to keep this extra digit for now, but I'll just keep in mind that this numerator now only has 1 significant digit. And we have 4 significant digits in the denominator. And when I do this division, I get 0.00032. The grams cancel, so this is just 0.00032 with 1 significant digit, so I underlined it there. Now I've gotten a little bit ahead of myself. I've just been working on this part, and I've been not writing this part because I was a little bit short on room. So we're going to take the answer to this, which is 0.00032 with just 1 significant digit, and we're going to multiply that by 100%. 100% is really 1 because percent means out of 100. So 100%, I know a lot of people have trouble with percents, but 100%, what percent means is out of 100. So what we're saying here is 100 out of 100, which equals 1. So multiplying something by 100% doesn't really change the value, it just changes how we express it. So what we're going to do here is multiply this number by 100 and keep the unit percent to show that this percent sign means out of 100. So instead of writing 100 in the denominator, we're going to write it as a percent sign. So 0.00032 is actually 0.032%, because this percent means to divide by 100. So if you divided this by 100, you would get back your original number. So this is 0.032%, and we'll go ahead and now round it down to 0.03% to take care of the significant digit and the uncertainty. So our percent error, let's put it in a different color. So our percent error is 0.03%. So this is a pretty good balance. It's not very far off at all. Way less than 1%, even less than 0.1%.